So now that you covered the fundamental theorem of algebra, which states that the number of roots will always equal to the degree, and there is no more roots than that, and not fewer roots than that, we're now going to make a couple of conjunctions or corollaries to this. So think about it this way. Recall that a polynomial is defined as a function that consists of many terms, but each term needs to be in this format right here, this a x to the n format, such that a has to be an element of real numbers. It just has to be real, and n is an element of, well, we would say natural numbers or whole numbers, because in order for it to be a polynomial, it kind of needs to have at least like two terms. So when I say natural numbers, it means there's always going to be one term that doesn't have an x value attached to it, like a constant, and then at least one term that has an x, and that'd be a polynomial. So I would like a polynomial with these roots over here, 0, 1, and negative I. If I create this, it's going to be x, that's the root of 0. Then to get the root of 1, I would need an x minus 1. And in order to get the root of negative I would need an x plus I. So again, just going bare minimum, in order to have these roots, this is what I would have. To write this polynomial in standard form, I will need to distribute these a little bit. So I'm going to distribute this. Standard form means no multiplication there. So x squared minus x times x plus I. And then that will equal to x to the third minus x squared. And then it's going to be plus x squared I. And then minus xi. So, question is this a polynomial? Well, let's look back at the definition. A polynomial is a function that consists of terms in AXN format, such that A is an element of real numbers. And what do I got here? These are imaginary components. So, is this a polynomial? No. No, due to these guys. It cannot happen. So, how can it become a polynomial? Well, it can become a polynomial by us removing the i's. So, how do you remove the I? Well, we've had this problem before. We just saw it a little bit differently. We used to look at things in this format like 2 plus I, for example. And the question was, how do I remove the I from the bottom? And the answer was, dun dun dun, conjugates. You multiplied this by 2, you multiplied this by 2 minus I, and then that took care of the imaginary component. So what we're going to do here is we're going to do the same trick, is we're going to take x plus I, and we're going to multiply it by x minus I, which gives us x squared plus xi minus xi, and then minus I squared, which really will turn into that real number of positive 1. Okay, so here is the logical path outline. Is every time you have a single imaginary root that has, you would have an imaginary coefficient, like you would basically end up with one of these things right here on top, right? That's what I'm saying. And since the polynomial cannot have those imaginary coefficients, the function would not be a polynomial. To make it a polynomial, you would have to negate, which means to get rid of, this imaginary coefficients. Well, the only way to get rid of it would be through a complex conjugate, which basically is just a conjugate with a complex with an I in it. So that means every complex 0 has to be paired up with its conjugate. And it brings us to this little theorem, complex conjugate root theorem. If p of x is a polynomial with real coefficients and a plus bi is a root, then its conjugate, a minus bi, must also be a root. Which brings us to the sample problems, and you would say, okay, well, look, I have a polynomial that has these zeros. Well, that would imply I would have an x minus 2. That's fine. I would also have an x minus 3i. But if that was it, I would have imaginary components. So I must add an x plus 3i to get rid of those imaginary components. And therefore, this must have this extra 0, and this must be at least a degree 3. Right? In this case, this is the same thing, but if I have a 2 plus 3i, I must also have a 2 minus 3i, which once again makes it a degree 3. In this case, since these two are not conjugates of each other, I must also have a 4 minus I and a 4 plus 2i. So that means this will be at least a degree 4. And looking at this one, which I really like, it's kind of a neat little, hidden question, is if you were to take this right here and factor it out, it would be now I would have to have a 2 plus I and then a 2 minus 2i. So those components would be kind of necessary in there. I know that you could potentially factor out a 2 and it would be a 1 plus 1i, but you would have to have an x minus in front of it, which you will not be able to get rid of this. That's what I was kind of thinking. I'm like, oh, maybe we can take it out, but you can't. So this would still be a degree 4. All right. So in sample problems 2 here, we're basically discussing, what is the least possible degree, and this would be the multiplicity. So you have x minus 1 squared, you have x minus 2 cubed, you have x minus I to the first power, but then you must also be adding an x plus I, which means you would actually have a degree 1, 2 from the front, 3 over there, 5, 6, and 7. So this would be degree 7 function. And, looking at one of these other ones right here, maybe a little bit below, is if you have 0i, well, that would be like x minus 0i, but that's the same thing as x. So like that doesn't have to have a conjugate, because 0i is not an imaginary number, really. It's still in a real axis. Then this guy over here will have an x minus 3i to the first power, and this would have an x plus 3i to the second power. Well, these two are already conjugates, but I have an extra one here. So what I need is an extra one of x minus 3i, and that means my degree will be 5. There will be 4 imaginaries and then 1 real one, that x. All right, so it has a rather neat corollary, and this is just kind of like, this has helped me save some time. So if you think about it, if px is a polynomial, we'll notice that here I'm saying rational coefficients, which means if you know not to expect irrational coefficients like roots, and you have a plus b as a root, with a being some rational number, but b being an irrational number, remember that the i's get canceled out with conjugates, but so do square roots. So this implies that you must also have the conjugate to cancel it out. So what I mean by that is, if you know that this thing over here is a polynomial, and it has all nice coefficients, like no irrational coefficients, so no square root of 2 coefficients, then you'd say, well, I know that x minus 2 has to be a root. I know that x minus 3i must be a root. I know that in order to balance out this 3i, I need to have an x plus 3i to make sure that coefficients are real. So that's necessary. But I also have this guy over here to balance out, and that would be an x plus square root of 2 to make sure that I don't have I don't have irrational coefficients. So again, irrational coefficients don't make it not a polynomial. It can be a polynomial with irrational coefficients, but most of the time, or the polynomials that I generally see, they have rational coefficients. So if you know that you're going for something with a rational coefficient and you see this, you automatically know there's going to be another one. So then my assumption would be that this is degree 4, assuming that this has all rational coefficients. If you're allowed to have non-rational coefficients, like square root coefficients, then the least degree would be 3. All right, that's it. Take some practice problems. Answers are on my website. Good luck.